So after all the work we did on the drive, it's actually ran very well since then. I think the added lubrication we did on the spindle flywheel down here's bearings is what actually stopped the squeal. Drivers work just fine. That squeal I had has gone away. The capacitor, the recap, has been successful, and I've used the drive and I'm very happy with it. But now we get into where things get more interesting for me in some ways, and that is, can I improve the drive? And there's kits out there that improve the performance, those kind of things. But I'm looking specifically at the power supply, and it's taken me a while to wrap my head around why these two diodes are here, why they get so warm, and what this extra filter capacitor is. Which is, which one here? C71. So this guy, C71? 4700 appears to be that guy right there. Anyhow, it's like, what are they doing here? And I'm too used to thinking about regular linear power supply design, where I've got a transformer driving a diode bridge. So the transformer in this case is external, driving a diode bridge, and once this point here becomes negative, this point becomes positive, and you feed it to your voltage regulators, and you see that right here to the 7805. AC comes in, gets rectified, comes to a filter cap here, 4700 microfarad, 35 volt, another small cap 0.1. These are really common around these 3-pin linear voltage regulators. A voltage regulator that's taking whatever this voltage is and regulating it down to 5 volts. Some output capacitance, a power LED, and off to the system itself. Typically, the 12 volt would also be picked up from this same output, but in this case, in the Atari, it took me a while to wrap my head around this. It's actually not plucked directly off of the normal output here, and that has to do with the fact that I guess they didn't get a high enough DC voltage across the 4700 microfarad filter capacitor here to get enough overhead voltage in place for the 7812 to regulate. Old school 7812 probably requires 13.5 or 14 volts to get into regulation, back in the era when these were made, maybe even a little bit higher. And so they've essentially kind of built a voltage doubler here. Kind of. It's so weird to me, but they are tapping off this raw rail here. So I'm going to measure this rail and see what it is. I'm going to guess that it's 11.5 volts to 12 volts, maybe a tad over. I could be wrong. I mean, I'm thinking we saw 11 volts AC unloaded off of here, but it's rated 9 volts AC. So as there's load, that AC voltage will drop. I've got the forward, bias on these diodes. I've got some voltage drop there. I don't know, 11 to 12 coming in, which isn't enough to get a 7812 into regulation, so it's got to be boosted up. But that's creating a large amount of current flow through these diodes, and they're 4001, so they have a normal forward bias of 0.5, 0.6 volts. All of the current that's driving the stepper motor and everything is coming through this diode here. So, we got the 12 volt regulator, but all that current is being passed really mostly through here and discharging this cap. It's really odd. It's really, really odd to me. And this is what led to me, before I realized exactly what they were doing here, looking for some modern switching replacements for 7805s. And what I've got here is a couple of things. These are 5 volt, 3 amp voltage regulators. They're actually 3 amp. They don't need a heat sink. They're over voltage protected. They're over current protected. They're thermally protected. Looks like a decent little design. They're meant to be a drop-in replacement for a 7805. So you can see it here. www.easysbc.com is the gentleman's website. I actually picked these up on eBay before discovering I could have went straight to a store. They were very reasonably priced. While I was there, I picked up a couple of 12 volt 1 amp, which are the blue ones, and he threw in this 3.3 volt into my order. Just here's a gift, thank you, kind of thing. Which I was thrilled to get that. So it'll be useful. So the question becomes, what kind of overhead voltage do these require? And what he basically says on his website is the input on these can be up to 13 to 40 volts. And I'm not quite sure how to interpret that. I've actually asked him the question. But I'm guessing these have a lower overhead than potentially the 78012 in here does. I don't know that for sure. So the first thing to do, like I say, is to get in here and make some DC voltage measurements. And so let's do that. So we've got the DVM here. When I looked earlier, it appeared we were getting, it was visible on screen. Hopefully it still is. Let me get on a ground here. In this case, well, there's a lock washer there to this metal. We determined this was ground, so I'm guessing that is a good ground. I've got 4 diodes here, which are the bridge. So this bridge rectifier here consists of these 4 diodes down here. CR17 and 18, are they actually labeled? Probably underneath the silk screen. I can't really see it. If we come to CR15, is going to be one of these 2 guys here. So CR15, this end right here, so away from the band, would be this point right here. So is that diode? So I should be able to measure there and get an idea of what the DC voltage coming to the 3.3 or the 5 volt regulator is. So let's go ahead and power the unit up. We should see the head step here. And we did. And the unit's powered up and running. So if I go ahead and measure the voltage here, I'm seeing 11.6 there. So it doesn't even get to the 12 that we need. So now I'm wondering if I need a boost regulator, because there's just not enough voltage at that point to be able to drive, honestly, a normal 12 volt regulator. So what do we end up on CR16 on the band end? So down here is what that boosted voltage into the 78012 is. My God, that's 23 volts. Wow. I don't know what kind of current that's good for. That's a little insane in my opinion. So I'm going to click on there so that I have the lead actually attached. 23 volts. That means that 12 volt regulator is dissipating 11 volts. And we'll talk about linear voltage regulators here in a second and why that's important. I'm going to cycle the power here and get the heads to step. So with the head stepping, we see it drop down towards 19. Wow. I didn't realize this little boost here was actually pushing it up by over 10 volts. You know, my guess is they had a ton of these 9 volt transformers, and rather than go to a 12 volt transformer, which would have done away potentially with these 2 diodes, you know, that capacitor and these 2 diodes, it could have completely done away with those. They chose, I'm guessing they had tons of those left over, is why the design is, rather than, you know, retool and build a bunch more of these that were, you know, 12 volt. Wow. So that is really interesting. It's sitting at 22.5 now. So I'll bet, is that because things are getting warm here? That is distinctly possible. I really don't want to stick my finger in there to find out. I don't know if I can actually get on the body of one of these. I'm going to have to tilt this up to do this. So according to this, that diode is just above ambient, as is that one. 29, so these are getting a little bit warm. Again, no surprise, but at this point the drive isn't under heavy use. You know, ambient's 23 here at the moment. So that's 27. So, you know, it's warm, but it's not like it's a disaster waiting to happen. The 12-volt regulator is sitting at, up here where maybe you can see it, 37 degrees C. And we're not actually stepping the drive at this point. I don't know what I would need to do here to actually cause resets to get that head to step. I hate cycling the power like this. That is the 7812, right? Yeah, it's the 7812 sitting there. Unless that was the 12th week of 78. No, UA 7812. 36. So it's not a huge amount of heat, and it is on a large heat sink. So the question becomes, is what I'm thinking about doing here even worth the effort? Those are a little bit warm. I had been under the impression from what I'd seen that those get really, really warm. I'm guessing with a lot of runtime, he would get warmer. I can go down and actually power this up and exercise it and measure that. Don't know if this effort is really worth it or not. It's interesting that there's a spring missing, and maybe it's always been missing. I'd never noticed before, but there's a, sorry, complete little tangent here, completely off in a different direction. There's a hook with a notch here, and there's a hook down here for a spring to be mounted between those 2 points, just to create some additional downward pressure here. Not that it's needed, because what loads the pressure of the capstan follower here is actually the tension through the metal here. It's really this flexible piece back in here, but that's a complete tangent. Let's set this aside for the moment. We've maybe talked about this in previous videos, maybe we haven't. Well, let's talk about linear voltage regulators. And, you know, actually I did get deep into this in the Altair 8800 stuff when we modified the power supply in the Altair 8800 to move heat off of the PCBs and into the back of the case. But anyhow, kind of here we go. We've got our transformer plugged into the wall. We've got our diode bridge. Let me actually draw this correctly this time because I got it wrong last time. Draw it like this. And the diode bridge should go to here and here. And the diodes all face this direction. When I try to draw this out of my head, for whatever reason, I always get it wrong. This comes off. This comes off. We come to a cap, and the negative should be down, and it is. This point is actually ground. So let's kind of talk about what's going on here. When we're in one half of the AC phase, and this wire is positive, and this one negative, the current flows. Remember I'm talking current flow here. Current flows against the diode to the negative side, and then back through to the positive side. And if you want to talk not current flow, but charge flow, if this is positive, the positive charge flows with the arrow to the cap, and with the arrow back to the transformer. When these reverse, and this is now negative, again, we'll talk about it in charge here, and this is positive charge. The charge flows, again, we're positive here to the top of the cap, the positive, and back to the negative side. So that's what's really going on here, is it's taking, if this is ground, the incoming AC, and if we look at the output of the transformer, we're getting this. Well, at the output of the diode bridge, I mean, we're getting this. So this would be the output of the bridge, and this would be from the transformer. And that's how we're converting the AC out of the transformer to DC, is this pulsating DC. So this now comes off in the circuit to a 7805. We'll just draw it as an 05. Again, they call this ground. It's the same thing. This is like a large capacitor. There's a small disc cap sitting here as well. It's typical in these older designs. There's another small disc cap here in this design. Let me actually make these connections. We come out to our load, and it's a resistive load. This is our load. It is everything that consumes 5 volts inside of the power supply. So we measured plus 11 point, I'm going to say 5 here. It was 11.5, 11.6 coming into the regulator. We want plus 5 volts out. So let's say the load is drawing a full 1 amp, because it'll be easier to work with. It's not actually probably drawing that much here, but let's call it 1 amp. So 5 volts, so power equals E times I. I is the current in the circuit, E is the voltage. So power equals 5 times 1, so 5 volts times 1 amp equals 5 watts. So there's 5 watts of dissipation. That's 5 volts into a 1 amp load here. So 5 volts at 1 amps is 5 watts power dissipation, but the reality is we've got 11.5 volts over here. And so if we take the power, again, equals E times I, and we say power equals E is 11.5 volts times I is 1 amp equals, in this case, 11.5 watts. So what the power supply is happening to do is it wants to regulate to 5 volts, but it actually has to get rid of 11.5 watts of energy to get the circuit to the 5 volt regulation. So what it's doing is, if we take this 5 volts and we subtract it out of, oops, it's the wrong place. Actually, no, we can subtract it from there. If we take the 5 watts and we subtract it from the 11.5, we get 6.5 watts. And that 6.5 watts is being, I can't speak, or dissipated through the body of the voltage regulator into the big metal heatsink. So that's where the heat is coming from, is the unused voltage has to be gotten rid of in some way. And in this case, in a linear regulator, you get rid of that unneeded voltage by dissipating it as heat. That's just how linear regulators work. As long as there's been linear regulators, this has been true. It just is what it is. And so you can see that if the voltage here was 7 volts, it would only be dissipating 2 volts as heat, and the amount of watts it would be dissipating would be much less. Well, 6.5 watts will warm this up well over time. So you can find plenty of articles on this, but I'll hit it briefly. What a switching power supply does is take this little 60 hertz that we see here bopping along and changes it to a much higher frequency, like 300. I want to say what he's got here, we're running, I don't remember, 300 megahertz or something, but much higher. And what that means is, let me go a little bit further with this. Oh, it bled through. If we take this pulsating DC that's coming out of the diode bridge, and it's coming out of the diode bridge, and it's coming to this capacitor. So let's just go ahead and draw in the capacitor here. And it's coming to this capacitor, and the capacitor is smoothing this voltage out. So basically the peak voltage right here is being captured by the capacitor, and it's trying to hold its voltage at that peak, even as the voltage rolls off. And so with a load on the circuit, what ends up happening is the voltage, after the diode bridge, ends up looking more like this. It gets pushed back up, it comes down, it gets pushed back up. And that's because the circuit is drawing current off and emptying that capacitor. And that's why you need a very large capacitor for high current, is because as the AC, or the pulsating DC coming out drops, you've got to keep that voltage high enough to maintain regulation. And if you took an oscilloscope and put across the capacitor, you'd see, we'll draw it again here. You'd see something like what we've drawn here, then back up to the peak, and then back up to the peak. And there's going to be some kind of delta voltage here as voltage is used. Well, if you take this and make it very high frequency, these little peaks where it drops off become very tiny. So you're not worrying about having a ton of capacitance to try to maintain high enough voltage between those two peaks to keep the circuit operating. So the amount of capacitance you need drops way, 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 way down. And because you're controlling the pulse width or the amplitude of this, however the circuit does, is you can get these pulses to provide exactly what the circuit needs, in this case 5 volts, and not have all this overhead that has to be thrown away. So switching power supplies are, it's been described 1,000 times, are more reliable, or not more reliable, they are more effective is the wrong word. What's the term here? Switching power supplies are oh, an old man's brain here failing. I can't get the word out. And they work better. They dissipate less heat. They're more efficient. Boy, there's the word for me. They're more efficient, and they can be much more efficient. Where this circuit here probably is less than 50% efficient. There's so much, there's 6.5 watts being thrown away here as waste to get 5 watts into the circuit that is required to operate the circuit. That's less than 50% efficiency, whereas in a switching design, you're getting 85, 90, or better percent efficiency, so a lot less heat. There's a lot less delta here. Described that really poorly. So I'm all the way back to my original question. Is it worth trying to convert this over to use switching regulators? If I dumped in 12 volts AC, I wouldn't need this craziness right here. So those 2 diodes, and that capacitor wouldn't be needed. Instead, the input of this regulator would just be tied right to the same place the input of this regulator is. That, however, means that the voltage here, rather than being 11.5 volts, would be higher. Say it becomes 13.5. Means there's more heat being thrown away with the linear regulator there. That allows the 12 volt regulator to work. But if these were switching and we're getting to 85% efficiency, there's not a lot of heat being generated. So 3 components could be removed, 2 of which, these 2 diodes, which are these 2 guys here off the board that supposedly get really warm and fail, would no longer be there. One of the capacitors would no longer be needed. Downside is I'm taking the wonderful Atari transformer and I'm replacing it with something that hasn't got the beautiful Atari logo on it, etc. Don't know that it's worth it. I could certainly put that 5 volt switching regulator, drop it in here as a replacement. It would remove that 6.5 or so watts of energy that are being dissipated into the heat sink. If I put the switching 12 volt in, because that's the same, if we do that same math for the 7812, it's going to be even worse. We'll call it plus 23 volts in, plus 12 volts out. Again, this regular is good up to 1 amp, so I'm going to make the calculation at 1 amp. It's going to be, the current's going to be less than that, and so the power dissipation will be less. The same was true for the 5 volt. But if it's 1 amp, we're going to have ultimately here 12 watts being dissipated here, and we're going to have 20 23 minus 12 is 11. We're going to have 11 watts dissipated here. Am I doing that right? 12 volts at 1 amp, power equals E times I, is 12 watts. And the delta in voltage is 11 volts. The 1 amp lives here the same way it lives here. It's got to be drawn from someplace. And so I could get rid of that 11 watts. I could remove, as high as, what did the math for this side say? 6.5. We could remove the majority of his max of 17.5 watts of heat from being dumped inside of here. It's going to be less than that, but the heat's just not even being generated because the switching regulators perform better. Switching regulators don't really need all this huge bulk capacitance either. Replace the two to remove a bunch of heat from inside of the case. You know, that doesn't sound like a lot of heat energy, but it is. I'm sure this heatsink gets warm with time. Hell, it's warm now. Just sitting here idle. This 12 volt side is warm. So how warm is that? Wow, I'm actually surprised it's not even... Let's measure in 29 degrees, and that's because it's a reflective surface. It is definitely warmer than that. Let's take a look at these diodes again. They're measuring 29 as well, which I don't believe. 5 volt regulator is at 43 degrees C. Let's see if I can get on this regulator. It's measuring 32 degrees C, so the 5 volt regulator is definitely dissipating more heat here, but it feels cooler over here to me than it does here. This is just approaching warm enough to be uncomfortable to touch. That is the 12 volt regulator down there, right? I shouldn't be moving this around with the power on. Yep. Oh no, 7805 is over here. That's the mistake I'm making. So the 7805 is over here. And it's warm, and that's because that 7805 is dropping 6.5 watts, up to 6.5 watts continuously into the heatsink. I don't know what the actual current draw is here. To measure it, we'd have to break into the circuit, and I don't really want to do that at this point. There's no great place for me to break into it. So I'm not going to do that at the moment. That idle heat right there, oh, that is hot. Why? Well, the package itself isn't super warm, so it's still dissipating heat well. One of these should be... No, they're both positive regulators. So the center pin on both is ground, which is why there's no mica tabs under these. I don't see any evidence of heatsink compound on either of these. Oh, there's a little bit under there. There's a little bit, so that's helping. So the thermal compound's helping get the heat out of the package into the heatsink. Well, now I'm really tempted to go ahead and replace both of these with the drop-in. This is a 5 volt 3 amp. It's going to have no problem. It is going to drop directly in. Same thing with the blue ones here, the 12 volt. There's plenty of room for it to drop directly into there. I don't need the PCB. Doesn't need to be attached to anything. This is good for 5 volts at 3 amps open air. And open air on these as well, the 12 volt 1 amp. They don't need heat sinks. They don't, potentially I could use a little bit of double-sided tape maybe to mount these to the heat sink for mechanical support. Not even sure I really need that. So what do you think here? We've talked this through. We've discovered that things really are getting warm here. And I suspect if the drive was being heavily used, we'd be creating a lot of heat over here as well. By going to these regulators, the switching, which are much more efficient, we shouldn't be we're not going to dissipate as much heat in the regulators. Are we going to make this circuit work as hard? Yes, we are. So, well, don't know. I'll think about this some more, and either the next video will be me replacing these, or we'll be talking about something else. I'll see you then.